Hi, my name is Itamar Turner-Trauring, and today I'll be talking about small big data, what to do when your data doesn't fit in memory. Before we begin, I'd like to talk about the most important question in any software project, whether or not it should be written at all. If your code is hurting people, if your code is hurting the environment, then the better you are, the more effective you are, the faster your code, the more efficient it is, the more damage you're causing. So before you start your project, before you start writing any code, make sure this is actually code that deserves to be written. And for the rest of my talk, I'm going to be assuming that you've already made that decision. So the problem I'm going to be talking about today is what to do when you have too much data. You have, let's say, a CSV with some data, maybe an array, and you try it out with some small amount of data and everything works fine. But then when you load the data with real data, it's 2 gigabytes, 10 gigabytes, 200 gigabytes, your program crashes. And the problem is, if you only have 16 gigabytes of RAM, you can't load 100 gigabytes of data into RAM. And so that's a problem that we'd like to solve. And so one solution is a big data cluster. You're going to need a cluster of computers. You're going to have to set it up somehow. You're going to have to quite possibly learn a new API, and then you're going to have to rewrite all of your code. And this is an exaggeration. I'm being unfair. You can get clouds of clusters of computers in the cloud and so on. But the transition from your normal code running on your computer to a large cluster is somewhat jarring. It requires work, it requires effort, and ideally we would like to avoid it. And in particularly, I'm going to be focusing on some assumptions that you have a single computer with minimal setup, and ideally you're using your existing API, existing code. Basically, you're just using your normal computer to process lots of data. The term for this is small big data, which is due to Alex Voss, Ilya Livov, and John Lewis. And they have a small big data manifesto linked here when you read the slides that you can hear about. And so before we go on to solutions to this problem of having too much data, you might be wondering, why do we need to actually load our data into RAM? We have a hard drive. Our data fits on the hard drive. And you can read and write to the hard drive. So why not just read and write directly to the disk and bypass RAM altogether? And the reason is that your hard drive, even the more modern, much faster SSDs, are still much, much slower than your RAM. So reading from SSD might take 16,000 nanoseconds, reading from memory 100 nanoseconds. So if you process your data on disk only, and you can do that, your code will run about 160 times slower. And if you're okay with that, great. But most of the time, running our code 160 times slower is not what we want. So if you want your computation to be fast, you have to fit your data in RAM. You have to load some data into memory. And so one solution is to spend more money. You can spend more money, get more RAM. So you can go off and buy a new computer. I just randomly did some price checks. Prices might be different. You can probably spend less money than this. This is just examples. But you can buy a workstation, 6 cores, 64 gigabytes of RAM for $1,000. You can also rent a computer, get a virtual machine in the cloud. And so, for example, you can get a machine with 64 cores and 432 gigabytes of RAM for about $3.60 an hour. And again, you might actually be able to pay less than that. And so in a lot of circumstances, because your time costs money, you could just throw money at the problem by buying a computer, by renting a computer, run your code, just get more RAM, everything's fine. You don't have to change any of your code. So it's worth keeping in mind does exist a simple solution. The problem, though, is that this solution of spending money doesn't always apply. For example, I once, at a certain job, we were running large batch jobs, and I calculated how much money we were spending on computation costs, on renting virtual machines. And the money we were going to spend on compute was going to be basically our projected revenue. So we would have no money left over for anything, including, for example, my salary, which I care very much about. So I needed to reduce the cost of the virtual machines we were using, which means I needed to reduce the CPU usage, but I also had to reduce the memory usage by quite a lot. So in many circumstances, spending more money is not the solution you want to take. You want to change your software to use less RAM. And for the rest of my talk, that's what I'm going to focus on. And in particular, I'm going to focus on 3 techniques: compressing your data, processing your data in chunks, so loading a little bit, processing, loading a bit more, processing a bit more, And finally, indexing your data. So you only load the data that you actually need, and the data you don't need doesn't take up any memory. So for the rest of this talk, I'm going to focus on these techniques, and in particular, I'm going to talk about them in the context of two libraries, NumPy and Pandas. The implementation of these techniques are not exhaustive. At the end of this talk, I'm going to link to my website where I have articles that expand on this talk. I talk about some techniques I don't actually cover in this talk, just limited time. It's worth keeping in mind that the fundamental techniques apply across the board because they come from the nature of how you process data, the nature of the hardware, and just how algorithms work. And so other libraries, other systems will use the same techniques. So even if you're not using NumPy or Pandas, these techniques will be useful. And finally, the techniques I'm talking about are fairly generic, but if you have specific data, you might be able to come up with your own custom variation. So if you have a certain type of data, it might compress very well. And you, as the person who understands the data best, will be able to come up with those variations. And we're going to start with compression. And the idea with compression is you take some data and you represent it in a different way than you normally would so that it uses less memory. And you can do this in a lossless way, where the data that you have compressed is identical to the original data, or you can do it in a lossy way where you're losing some details. And presumably, if you're losing some details, you'll try to only lose the details that don't really matter too much. And I'm going to be talking about lossless compression, but if you go to my website, there's an article that talks about lossy compression. And just to clarify, when I talk about compression, you might be thinking about like a zip file or a gzip file that is compressed on disk. And the problem with a zip file is that in order to do anything with the data, you have to uncompress the data. And then once it's in memory, it's no longer compressed. So I'm not talking about things like that where you have compression on disk. I'm talking about compression in memory. So let's start with NumPy. NumPy, if you're not familiar with it, is a library that lets you store multi-dimensional arrays, one-dimensional, two-dimensional, three-dimensional. And each array has a type, a data type. You can store integers, you can store floats. And you can, when you store an integer, there's different kinds of integer types. You can store a 16-bit unsigned integer, which lets you store values between 0 and 655,000, etc. Or you can have a 64-bit unsigned integer, and then it can store data between 0 and a very large number, which is 2 to the power of 64 minus 1. And so 64-bit integers let you represent much larger numbers, but as you'd expect, they also use 4 times as much memory as a 16-bit integer. Let's look at an example. We have an array we're going to create 2 arrays in NumPy. It's just going to be full of ones. And it's a 2-dimensional array, 1024 by 1024. And the first array uses 64-bit integers, and the second array uses 16-bit integers. And we can look at how many bytes of memory each array uses. And the first one uses around 8 megabytes of RAM, and the second one uses 2 megabytes of RAM. So as you'd expect, using 64-bit integer uses 4 times as much memory as a 16-bit integer. So if your data fits in a 16-bit array, if all your numbers are going to be less than 65,000, you should just use a unsigned 16-bit dtype, and you're just going to reduce your memory, in this case, by a factor of 4. Another approach to compression, which only works, again, on certain kinds of data, is sparse arrays. So imagine you have an array that's mostly zeros. If most of your data is zeros, storing all those zeros in memory is sort of a waste of time. You can just store those values that aren't zero and say, if we don't have that information about this, just assume it's 0. And this particular library, the PyData sparse library, implements sparse arrays. And it implements in a way that interoperates with NumPy arrays. It supports a subset of the same API. You can multiply them by each other. And it supports different representations. And in this case, I'm going to show you an example. It's using sparse coordinates. And the idea is you have, let's say, a large array, and let's say it's showing you location of stars in the sky. And so in much of the sky, you'll have darkness. It's not a very good telescope. And in a few places here and there, you're going to have stars. And so really, you don't have to store the whole array's values. You only have to store those few locations where you have a star. And basically, you're going to be storing at this xy coordinate, there is a pixel or array value, depending on how you think of it, this value. To simulate that, we create a random array of 1024 by 1024. And basically, the random values will be between 0 and 1. And then any value below 0.9, I'm going to set to 0. So basically, 90% of the pixels are now black in our two-dimensional array, two-dimensional image. Now we can take our regular NumPy array and create a sparse coordinate-based array from it. And if we compare the memory usage, the sparse array uses about 1/3 of the memory of the regular array. It can't just, because it has to store all those XY coordinates, there is some overhead. And so that's why it doesn't work for if you have lots and lots and lots of dots in your array. But as long as the number of dots is low enough, the array's memory usage will be low. And it can interoperate pretty well with the regular NumPy arrays and have the same operations. So next, let's switch to pandas. If you're not familiar with pandas, pandas is a way to operate and process data similar to the kind of data you'd have in a spreadsheet or a CSV. Basically, you have columns of data, and each column has a name and each column has a type. So you might have address, that's a column, it's a string, and then say a GPS coordinate, XY, and then those two columns, the array type, the column type will be an integer or a float. And just like in NumPy, you can specify a dtype for each column, you can do the same in pandas. Pandas builds in NumPy. So if we just load a CSV from disk into a pandas data frame, by default, it's going to load the data and guess what kind of data type it is. And so for numbers, if it can't figure out what kind of, if it decides it's a number, it's going to use 64 bits for every entry. But if we know that all the values in that particular column are integers that are smaller than, let's say, 16,000, we can use a 16-bit integer. And so instead of using a 64-bit integer, 64-bit of memory for each entry in the column, we're using 16 bits of memory for each entry in the column. So we've, again, cut our memory usage for this column by 4, and it's storing the exact same data. So it's lossless compression. We haven't lost anything. So that was compression. And next, we're going to move on to chunking. And chunking is a way for you to reduce memory usage without actually loading everything into memory at once. In compression, we did load everything. With chunking, we're saying maybe we don't have to load everything. And the way to think about this is consider an array that has a bunch of values on it. We want to find the maximum. So one thing we can do is just load the whole thing into memory and just go through all the values and find the maximum. But we can also say, load the first half and get the maximum of the first half. Load the second half, get the maximum of the second half. And the maximum of the whole array is the maximum of those two values. So we've gotten the same answer, the maximum for the whole array. We only had to load half the data at once. And we could do the same thing with quarter data each time. So basically, just we load the chunks, operate on the chunks, and then maybe we combine the results. So when it comes to NumPy, you want some way to store the data on disk so that you can load only subsets of the data at a time. You need to be able to load only one chunk of the data, not the whole array. And one way to do that was a Zarr. Zarr is a way of storing data on disk and lets you set the chunk size that it stores on disk. And then when you load a chunk or two chunks together into memory or however many, it gets turned into a NumPy array. And then when you write that array back into the Zarr, it gets written back in the appropriate chunks. But you don't have to load the whole array just to process one part of it. So in this example, we're opening a Zarr. And we're loading basically from this one-dimensional array that has 1 million entries. We're only loading 1,000 items at a time. And we're running a maximum on each of those chunks separately. And then once we have the chunk, the maximum of all those chunks, we can do the overall maximum of all those chunks. That's the overall maximum of the array. And so we can calculate the maximum of the whole array without loading the whole thing. And if you look at a Zarr object that we've opened, its type is just a Zarr object. It doesn't actually load anything when you open the Zarr. It's just a pointer to some place on disk. And only when you actually slice it, only when you get a subset of it, does it get loaded into memory and you start using memory. Pandas also supports chunking, but you don't have to use a third-party library. It actually has a feature built in. So for example, if we want to load a CSV, previously we were loading the whole CSV into memory at once. What we can do is we can tell Pandas, instead of loading the whole CSV, I want to load the CSV in chunks. In this case, we're going to load 100 lines, 100 records at a time. When we do that, instead of getting a single data frame from Pandas, we get an iterator of data frames. Each data frame is 100 lines of the CSV. And so again, if you want to calculate the maximum, we just calculate the maximum of that chunk and then compare it to the overall maximum. And we have calculated the maximum of this column of the CSV without actually having to load the whole CSV into memory. We've only loaded it 100 lines at a time with very low memory usage. And the final technique we're going to talk about is indexing. So when you think about an index, think about the back of a book. Like you have a reference book, some sort of history book, and you want to know everything that happened related to everything in the book that's related to the Battle of Waterloo. So you go to the back of the book, and it's alphabetical, so you can easily find Battle of Waterloo. And it tells you Battle of Waterloo is mentioned on page 200. And so you flip to page 200, and you read that page, and now you know everything the book has to tell you about the Battle of Waterloo. And we haven't had to read the whole book. We just had to read the index, which is much smaller than the book because it's just a summary, and the actual part of the book that talks about the data we care about. So that's an index. And an index will let us get a subset of the data. And that is different than what chunking does. Like they set, in some ways, chunking and indexing might seem a little similar because in both cases we're loading part of the data. The difference is that chunking is something you use when you need to read all the data. You can't avoid it. You just don't want to load all of it at once. So if your question is, what's the longest word in this book? The only way you can know that is by reading every single page in the book. You can't read only page 200 and find the longest word in the book. You'll just find the longest word in page 200. You're going to have to read the whole book. But you can just load it one page at a time, find the longest word in that page, and then forget about that page. And that way you don't have to load the whole book into memory. Indexing is useful when you only have to load some of the data, not all, but some. So for example, you have an accounting system and you want to know how much money did we spend in July. You don't care about June, you don't care about May, you don't care about September, you only care about July. So you only want to load the data specifically for July. You don't have to load everything. In practice, you might actually end up using these two techniques together. For example, if your question is how much money did we spend in July, it may be that the data for July also is quite large. So yes, you can ignore all the other months, but you still have a lot of data. And so once you've found the data for July, instead of loading all of it into memory, you can load it in chunks, sum up the chunks, and get the answer. So you can actually use these new techniques together. And the simplest way to do indexing is to have a directory and have the file name for each of your data files tell you what data is in that file. So in this example, we have a different file for every month of the year. So we have a file for January, February, March, and so on. And so if you want to load the data for July, we only have to load 2019-joule.csv. We don't have to load the other files. And the index is basically just a listing of the directory's contents. And so let's see how we can use indexing with pandas. And we'll start with a simple piece of code that does not use indexing, and then we'll modify it to add indexing in. So let's say you have a CSV with the voter registration records for the people who live in your city. And you want to find the voters who live on a particular street. And so if you're going to do this with chunking, because you have a large file, it doesn't fit in memory, the way you do it is you'd say for every chunk, we're going to load, let's say, 1,000 lines at a time. For every chunk, filter by the street name, making sure that the street name only matches the one that we want. And we'll get a bunch of small data frames for the voters for particular streets, for that particular street. And we concatenate all those small data frames into one big data frame that has all the voters for that particular street. And if we wanted to only do this once, this would be fine. But we might want to run this function over and over again on different streets. For example, you're managing a canvassing effort, and one day you're going to this bunch of streets, and one day you're going to a different set of streets. And so you're going to be calling this function over and over and over again. If this function is slow, then that's all going to add up. And that is where indexing is going to be helpful. And the way we're going to index our data is by storing it in SQLite. SQLite is a SQL database, relational database, that is built into Python. It's a library. You don't have to run a server like Postgres or MySQL. You just have a file on disk. You load it up with this library that's built into Python, read and write to it. So it's really convenient to work with SQLite files, no different than working with a CSV file. And what we're going to do is we're going to take all the data from the CSV, read it in chunks, and then dump it into a SQLite database. And Pandas can do this automatically for us. It'll automatically create the SQL table. You don't have to worry about the columns and the column types. Pandas will do it for us. And then once we've loaded all the data into that SQL table, we're going to tell the database to create an index on the street column of the voters table. And SQL databases have a built-in functionality for creating indexes for fast queries. And we get to just reuse that functionality for our index on the street column. And because it's a SQL table, we can have as many indexes as we want. We can have an index in other columns. We can have indexes that are on multiple columns. We'll even be able to have indexes that span tables, although that's a more complicated use case. So now we have this file, a SQLite file on disk, and it has all the data and an index for fast queries. And now we can rewrite our function for querying voters for a particular street. But instead of loading from a CSV, we're going to load from the database. So we open a connection to the database, and we run a query saying, select all the rows from this table, from the voters table, where the street equals whatever value we've passed in. And then we tell Pandas to run this SQL query and turn the results into a Pandas data frame as normal. And so once we've called this function, we don't know that the data came from a SQL database, just like we don't know it came from a CSV. We just have a normal Pandas data frame. Because SQLite has an index, it will be able to find those rows that match this particular street really quickly and only load those rows. It's not going to have to read all the data. It's only going to have to read the data that we care about. So let's see a comparison of these two techniques, the chunking technique where we just load from the CSV and the indexing technique where we have SQLite run an index. And I'm using the voter registration database for Cambridge. It has about 70,000 voters. It's a pretty small number of voters. New York City would have millions. And if you think about memory usage, in the CSV case, we were only loading 1,000 chunks at a time, and then we accumulated the matching rows. So it really doesn't use much memory. In the SQLite case, it has to load the index into memory, but again, an index is a summary, so it should be pretty small. And again, we have the memory usage for the matching rows. So in both cases, the memory usage is going to be quite low. So we've solved our underlying goal of being able to process lots of data with only a little bit of memory. But the main difference between them is execution time. Loading the CSV took 574 milliseconds because we had to load every single row from the CSV and parse it and then match it against our street filter. With SQLite, we only had to load those records we needed because we had an index added to the table. And so it ran 50 times as fast, again, while still having very low memory usage. So that was our last technique, indexing. So what if you're using some other library, not Pandas or NumPy, and you have the same issues of too much data, not enough memory? Basically, the same root causes are the problem. Memory is fast, but it's also expensive, and disks are cheap but slow. And so the same basic solutions, compression, chunking, and indexing will be available to you. In fact, if you think about SQLite, SQLite doesn't have to work with Pandas at all. Any database doesn't have to work with Pandas. Databases solve this problem all the time, and they solve it in similar ways with compression, chunking, and indexing. And so now you know about these techniques, you can just read the documentation for whatever tool you're using and just look for those techniques and how to apply them in your particular circumstances. While the bulk of this talk focused on those 3 software techniques, don't forget that you have the option of spending more money to just get more RAM or rent a computer with more RAM, get a virtual machine. And sometimes that will be the cheapest, easiest thing to do. Finally, if you want to get the slides for this talk, here's the URL. And I have a prose articles with much of the content in this talk and even more techniques and strategies on my website at pythonspeed.com/datascience. Here's my email and Twitter handle. And if you found this talk valuable, just so you know, I do training. These days, it's going to be online training. So if that's something that interests you, if you'd like to upgrade your team's skills, then reach out. And more broadly, if you have any questions about the techniques I cover, about how you process lots of data with limited memory, please get in touch, send me an email, send me a tweet. I'm always happy to answer. Thank you.